Welcome to the Week 6 review for Math 2413. In this session, we'll be going over the product rule, the quotient rule, some derivatives of trig functions, and lastly, we'll talk about the chain rule. So let's go ahead and get started with the product rule. And we touched a little bit on this last week. So the product rule says that if we have two functions of x, let's say u and v are functions of x, and when we say functions of x, this just means there's something with an x in it, basically. And we wanted to take the derivative of these two functions multiplied with each other. Well, the product rule says how we can do that. It says the derivative of u times v is the derivative of u times v plus u times the derivative of v. And this is called the product rule. Very important, very useful. You will use it for forever, basically, so make sure you know it. Similarly, we have the quotient rule. This time, instead of u times v, we have u divided by v. And this derivative is v times the derivative of u minus u times the derivative of v all over v squared. And this is known as the quotient rule. And it is also very useful. So let's go ahead and do some examples using these. Actually, I'll talk a little bit more about the quotient rule. Sometimes this can be a bit hard to remember. So I usually remember it using a little mnemonic, low d high minus high d low over low low. And it just rolls off the tongue a bit better. So what this says is you take your bottom function, your low, multiply it by your high function, or specifically the derivative of your high function, and then subtract your high function times the derivative of low all over your low function squared. And that's just a little mnemonic. You can use it if you want. You can just memorize the formula too. That either will work. Just make sure you remember the quotient rule. So let's do some examples. Let's say we have f of x is equal to x squared times e to the x. If we wanted to take the derivative, well, what I notice is this is two functions of x, x squared and e to the x, being multiplied by each other. So I'm going to use the product rule. The product rule says I should take the derivative of my first function, so the derivative of x squared is 2x by the power rule, multiply it by my second function, then I add my first function times the derivative of my second function. The derivative of e to the x is just e to the x. So then that would be my answer. Now, if we wanted to do a different problem where we had e to the x divided by x squared, in this case, we have two functions of x, and one of them is being divided by the other. So we should use the quotient rule. Well, then the quotient rule says I should take my low function, multiply it by the derivative of my high function, minus my high function times the derivative of my low function, all over my low function squared. And that gets me x squared e to the x minus 2x e to the x all over x to the fourth. If I wanted to simplify, I could factor out an x times e to the x on top. That leaves me with x times 2 all over x to the fourth. And now I can cancel an x on top and bottom. And this would be my final answer. Any questions? Cool. And one thing you will notice is that whenever you can use the quotient rule, you can actually just turn that into the product rule combined with the chain rule usually. So for example, if I didn't want to use the quotient rule, I could rewrite g g of x as x to the minus 2 times e to the x. So the quotient rule is really just the product rule in disguise, but it's a lot more convenient to think about because we don't like to mess with negative exponents because sometimes they're difficult to work with, especially with more complicated functions. So remember the product rule and the quotient rule, and let's do some practice problems.
What would it look like with the negative though, using the product rule?
All right, let's actually just work that out then. So using the product rule, what should I do?
It would be the derivative of the first times the second term and then reverse.
Right. So the derivative of the first, so the derivative of x to the negative 2 is what?
Negative 2x to the negative 3.
And then times e to the x. And then I would add x to the minus 2 times the derivative of e to the x is e to the x, right? Okay. So if I rewrote this without negative exponents, right? If I found a common denominator now, it would be x cubed. Right?
So I guess my next question would be, how come we didn't carry the negative 2 down with it?
So you're wondering why on this step right here, why the negative 2 is on top and not bottom?
Yes, sir.
So the idea is maybe it's more of a matter of like looking at parentheses. We can visualize this as the negative 2 is only applied to the x. So when we bring down the coefficient, it's still applied to it, but the exponent isn't applied to the negative 2. So then we would only flip the x to the bottom. Make sense? Good question, though. But we're clear on this? And you'll notice we did get the same answer. This last step, I did kind of factor my e's to the x out, and then flip the order that I wrote my x and my negative 2, but it is the same answer. All right, practice time. Find the derivative. And not a ton of practice problems right now, but there will be a lot later on, so ready? And solve it with either the product rule or the quotient rule. It's up to you. It's give you maybe a minute more to work on these. All right, how's it coming? Any answers?
I'm still working on the second one.
All right. Any answers from the online people? All right. Perfect. What did you guys get? Plus 2x squared. 3x squared plus 3. Perfect, perfect. And x times 2 minus x all over e to the x. All right. Cool. Let's take a look. For this first one, there are several ways we can do it. It is a simpler derivative, so we could actually just multiply it out if we chose to. So that's one way you could do it. We're going to solve it by the product rule, though. For the first one, that's a different answer. Right, we aren't dividing, it's multiplication, so we'd want to use the product rule. All right. Perfect. So if we wanted to use the product rule, we could take the derivative of the first, which is 1, multiplied by, leave the second alone, plus the first times the derivative of the second, which is 2x. And of course, this is x squared plus 3 plus 2x squared, which is of course 3x squared plus 3. And you can see if we multiplied things out and then took the derivative, we would get the same thing. The derivative of x cubed plus 3x is 3x squared plus 3. So both of these ways match and we're good to go. For the second one, it's already set up to use a nice quotient rule, so we're going to do that. Quotient rule, we would do low function, e to the x, times the derivative of the high function, minus high x squared times the derivative of the low, all over e to the x squared. And now we need to simplify. I'm going to factor out an e to the x from the top. And on the bottom, I'm going to write it as e to the x times e to the x. And now I can cancel some e to the x's. And finally, I'm also just going to factor out an x on top as well. There you have it. Any questions? All right. Let's move on to some trig derivatives then, because I know that everyone has a bit of trouble with those before they've quite memorized them. So let's go ahead and review exactly what all your trig derivatives are. First off, okay, there we go. First off, this? Use OneNote. There we go. All right, that'll work. First off, the derivative of sine. Actually, we're going to put these all in general forms, so using the chain rule already, and I'll explain more what the chain rule is later. The derivative of sine is cosine, and you always leave the inside alone. You would then multiply by the derivative of the inside. The derivative of cosine is negative sine. And again, multiply by the derivative of the inside. The derivative of tangent is secant squared. And then we would have all of our other derivatives, the less common ones. We could have cosecant, which is 1 over sine. Its derivative is negative cosecant of u cotangent u multiplied by 2. The derivative of secant is secant u tangent u du. And finally, we have cotangent. And the derivative of cotangent is just negative cosecant. Negative cosecant squared, sorry. All right, a lot to remember, huh? One helpful tip pointed out by one of the students is that all of the ones that start with a C have a negative. So here we have a cosine, here we have a negative, here we have a cotangent, here we have a negative, here we have a cosecant, here we have a negative. So that can be a helpful way to remember which ones have negatives on them. Another thing you can do is if you forget one of the less common ones, such as a derivative of cosecant, you can actually use your derivatives of sine and cosine to figure those out. So let's say we wanted to find the derivative of cosecant. Well, cosecant is just 1 over sine. Now we can actually use the quotient rule because we have a quotient here. We have 1 over sine. The derivative would be sine of x, our low function, times the derivative of our top. The derivative of 1 is 0, minus our top function, times the derivative of the bottom. The derivative of sine is cosine, all over sine squared. This, because it's got a 0 here, that just goes to 0. So we have negative cosine divided by sine of x times 1 over sine of x. All I did is I split up my sine squared on the bottom and rewrote. So then negative cosine over sine is negative cotangent, and 1 over sine is cosecant. So this would be our derivative. So that's something you can do if you forget some of the less common ones. You absolutely have to know these two though, and it's probably best to just memorize all of them. All right. Example problem, I guess. Okay, 3x. All right. If I wanted to take the derivative, again, I have a product because I have x multiplied by cosine 3x. So my product rule tells me I should take the derivative of my first one, multiply it by my second one alone, plus my original First one multiplied by the derivative of cosine 3x. The derivative of cosine is negative sine. As always, I leave my inside alone and then multiply by the derivative of the inside. The derivative of the inside is the derivative of 3x. The derivative of 3x is 3. Now just cleaning it up a bit. There's my final answer. Make sense?
Is there another way of doing it? 'Cause I don't think I've ever seen my professor do the multiply by the derivative.
Like this part?
Yes, sir. I don't think I've ever seen that before, unless I'm just confused.
So technically this is the chain rule. I just like to introduce it now because then you already have the completely general forms of the derivatives of sines and cosines, trig identities. But you have covered the chain rule, right?
Yes, sir. I was
Um,
curious about what the other way was.
Yeah, I don't know if I don't know if I've seen the other way how your professor would have done it. Interesting.
I'm probably just confused.
It's possible. I can take a look at your notes in a little bit. Well, let me take these practice problems if you like. But let's see. Perfect. All right, time for some practice problems. Of course, you're just supposed to find the derivative. This one is a bit trickier. I'll give you guys a few minutes to work through those.
I'm probably just confused. Specifically for the problems. So I think that's what we just did.
Yeah. Online people, how's it looking? Any answers? All right. Cool, cool. Well, let's see, what did you get? All right, let's start going over these. For this first one, I gave you guys a bit of a harder problem. Kind of rude of me, I know. But clearly we've got, all right, nice, nice. Let's go over this first one. So we do have the product of two separate things. We're going to be using the product rule. So by the product rule, we would say the derivative of our first function is e to the x, leave our second function alone, plus our first function multiplied by the derivative of our second function. Now, the derivative of sine of x squared, well, we have a function, or a formula that tells us what our derivative of sine is. The derivative of sine is cosine multiplied by the derivative of whatever's inside. So the derivative of sine of x squared is cosine of x squared multiplied by the derivative of the inside. So the derivative of the inside is the derivative of x squared. Derivative of x squared is 2x. Now, I suppose we could simplify this a bit just by factoring out an e to the x, and this would get us sine of x squared plus 2x cosine of x squared. All right. For part B is fairly straightforward. What we have is 3 times the tangent of 2x. Again, we do have a formula for the derivative of tangent. The derivative of tangent is secant squared of u times the derivative of what's inside. So derivative of 2x is just 2. Did I forget the e to the x for the cosine of 2x on part A? So what I did is I actually factored my e to the x out, so it's being distributed to both of these. I just wrote that way. So it's in there. Yeah. And then, right, 6 secant squared of 2x is what b simplifies to. And then for part C, there are actually, again, a couple of different ways we could solve this. I bet most of you probably use the product rule. So let's go ahead and use the product rule. And then I'll show you guys another way we could have done this. The derivative of sine is cosine. Leave the second function alone. Plus our first function, sine of x, times the derivative of our second function, derivative of cosine is negative sine. And that goes to cosine squared x minus sine squared x. Well, another way we could have done this is using a trig identity. One of our trig identities is that sine of 2x is 2 sine of x cosine of x. So what this means is if we divide both sides of this identity by 2, 1/2 sine of 2x is equal to sine of x times cosine of x. So instead of taking the derivative of sine of x times cosine of x, I'm going to take the derivative of 1/2 sine 2x because they're the same thing. So I would have 1/2 times cosine of 2x multiplied by the derivative of 2x, so times 2. And this is just cosine of 2x. So this is actually my derivative as well. And you might be looking at these and thinking, These things are pretty different. The thing is, this is actually another identity. Cosine squared minus sine squared is cosine of 2x. So that's just a couple of trig identities. This answer is also fine, also correct. They're the same thing, but this is just another way of solving for your derivative.
And that is technically the product rule. You just left off the other side because it equates to 0, right?
Right here?
Yeah.
Um,
Isn't technically wouldn't the derivative of a half be 0 and then you just left it off?
right.
Okay.
We could technically think about multiplying by a half the product rule, but again, that's also one of our actual derivative rules. We covered it, I think, in the last one. Let's see if I can find it. Right, so this is actually our constant multiplication rule. So we covered that right here. If you have a constant multiplied by a function, you can just pull the constant out. Good question, though. You could think of it as being a product rule. It's just a bit of extra work that way. All right. Any questions on these trig functions? Derivatives of trig functions? Not terrible. It's just you do have to memorize a bunch of trig derivatives. All right. Now let's talk about the chain rule. Because the chain rule is a whole lot of fun. And it's also super powerful and super useful. Oh, I'm still in highlighter mode. So we already know how to take the derivative of things like x squared, e dx, sine of x, simple things like this. But what we don't know is how to take the derivative of things like x squared plus 3e dx to the fourth, or sine of cosine of x squared. These things get a bit trickier. The chain rule, which I've sneakily been making you use a little bit, tells us what to do in these situations. So the idea is when we take a derivative, we almost work from the outside in. So if we were looking at this first thing, x squared plus 3e dx to the fourth, we would look only at something, I'm going to call it u, to the fourth. Well, this is just the power rule. We know how to solve that. All the chain rule says is whenever you make this kind of simplification, you have to then multiply by the derivative of what's inside. And what's inside in this case, we're calling u. So a quick example would be we work from the outside in. First, we'd multiply 4 times the inside using the power rule. And then we multiply by the derivative of x squared plus 3e to the x. Derivative of x squared is 2x. Derivative of 3e to the x is 3e to the x. And that's the chain rule. If we wanted to say it super formally, if f of x, that's a capital F, is a composition of two functions, then you can write the derivative as the derivative of your first function composed with your second function multiplied by the derivative of your second function. That's the formal definition. Personally, this is hard to look at for me. It's just a bunch of symbols, really. I like to think of it as we work from the outside in. So let's do another example, and then I'll set you guys to doing some problems. That's going to be f of x. Well, my chain rule says I should work from the outside in. My biggest thing is what is these parentheses to the 7th. I'm going to say this is the power rule. I know what to do here. Bring the power down as a coefficient, decrease it by 1. Now the chain rule says I should multiply by the derivative of whatever's inside. So multiplied by the derivative of 2x squared is 4x, derivative of 3 is 0. Make sense? Perfect, perfect. All right. Time for some practice problems. And again, you're just finding the derivative.
Quick question about that one. How come? So, because that 6 is so big, they don't want us to multiply it out. Go to the very.
Oh, goodness gracious, no.
Okay.
This is already in factored form. In general, it's acceptable to leave it either in a factored form or in a fully multiplied out form, fully canceled. It's really the in-between bits where some parts of it are factored and some parts are added that we really don't like. If you have a 6th power in there, yeah, that would be a whole thing to multiply out. We don't do that. Anyway, I'll give you guys a few minutes to work on these, and then we'll check them, see what one's going. It's just easier, right? That makes sense to you?
Yes. I don't know if I can replicate it, but I was going down the wrong path to start with. I'd done basically the power rule, just distributed the cotangent to the prime e, and then subtracted one from cotangent.
Right, but it's different since you're the exponential, right?
So, but thinking like from outside in kind of thing, how come you don't look at cotangent as an exponential function of itself? That's kind of where I got tripped up.
So, um, I'm not quite sure I'm following what you're saying.
So like, you know, how you said that you think about it from the outside in. So I was thinking of cotangent as the exponent, and then e was what's on the inside. So e was u. So how come you don't apply the power rule to cotangent since it is an exponent in this case? It's the outside.
Well, the power rule only applies when you have a constant as a power,
Okay.
right? Cotangent of x is a function. So the power rule doesn't apply at all.
Okay.
Let's see. Also, your cotangent of x is kind of contained within your e to the power of something, right? Smaller part of your larger function. I can't really see how you would. Like, I guess I can get where you're coming from. It's just that cotangent of x is a function, so you can't use it. That's how I want to just on words so that people wouldn't be tripped up on it to see why it's not working. Online people, how's it going? Good, you're finished? Nice, nice. What answers did you guys get? times 4x squared plus sine of x. All right. Okay. Fernando, looks like you're missing a squared. Let's go over part A. I'm guessing you probably just forgot to include it in your answer. So our chain rule says we work from the outside in. First off, we have a power rule. 3 times the inside. And then we decrease the power by 1. Then we multiply by the derivative of the inside. So the derivative of 4x squared is 8x. Derivative of sine x is cosine of x. Done. Not too terrible. Yes, don't forget your exponent. Needs to stay on there. All right, for part B, what did y'all get? All right. Negative cosecant squared x times e to the cotangent of x. Perfect. So again, this is the chain rule. It's a bit different, but our base function is e to the x. So the derivative of e to the x is e to the x. It doesn't change. So the derivative of e to the cotangent of x is e to the cotangent of x, but then we have to multiply by the derivative of what's inside, and what's inside in this case is cotangent of x. So then the derivative of cotangent is negative cosecant squared x. So then our first derivative is negative cosecant squared x times e to the cotangent of x. Any questions? All right. Now this third one, sine of e to the x over x. For this one, I'm going to call it h of x. Well, then our derivative, h prime of x, would be our outside function is sine of x. The derivative of sine is cosine of whatever's inside. And now we have to multiply by the derivative of the inside. Well, the derivative of e to the x over x, we need to use the quotient rule for, because we have a quotient. So that derivative would be our low function multiplied by the derivative of our top function minus our top function multiplied by the derivative of our bottom function all over our bottom function squared. And if we simplify that, there we have it. Make sense? All right. So that's the chain rule. Just kind of work from the outside in. Nothing terrible. For the rest of the review, we'll basically just be covering more derivatives, more practice problems, because the best way to improve and get better is just practice. So, give you guys a couple more practice problems. And do not bother simplifying this one, because that would be a whole mess. I'm just saying, don't simplify it. Work through it. Just to get you used to taking the derivative and using the chain rule, combining all your rules. Good luck.
Does precedence matter?
Yes, just write down the derivative in some form.
But I meant like, does it matter if we take the quotient rule first or chain rule first? Which one should we do first?
Well, what's your general form?
Chain rule then quotient.
Okay, so if you're going to use the chain rule, what would you do first?
You do 3, and then the x plus 3, and then the power of 2.
Okay, but is that contained within something bigger?
Yes.
Right, so you need to use your.
Quotient rule first.
And these derivative problems are pretty hard, so don't stress too much if you can't get them. I'm just trying to get you guys maybe used to looking at some of these harder problems. And of course, we'll work through the solution.
We stayed up last night just thinking of the worst thing you could give us. Just a little bit.
I was just thinking about the next exam problems.
Oh no.
Um,
There's just so much to think about.
looking at page 2. Page 2 might be worse. Yeah, the idea is take it just one step at a time. It's a lot to look at, I know, but half the problem is actually ignoring the other parts and just taking it one step at a time. So which one are you working on right now?
The numerator.
So which?
Oh, I was looking at E. I didn't even look at D. I didn't
Alright.
even see that.
All right. So I guess what do you think your first step on question E would be?
So I squared the denominator, then I put it up top. I left it as is. Now I need to take the derivative of the numerator, which involves chain rule. So I know it needs to be like 3x plus 3 squared.
Right. So you're using the quotient rule, right?
Yeah.
All right. Perfect. So you're taking the derivative of the numerator. You could even just write this out as a whole separate problem and say, what's the derivative of x plus 3 cubed times e to the 4x?
Okay.
It is, yes. It's going to be hard to work through and pay attention to all the little details.
You're a math major, this is fun.
Just a bit.
I struggled to sign in at first. I had to input my UTD ID like 3 times, and I scanned my card 4 times. I got in eventually. It just was a pain. Oh well. I'm just going to stump on whether I should take the derivative of them separately from the chain rule or whether I should. Because I know that you multiply by the inside derivative. So I'm trying to figure out whether I just do like derivative and then multiply by that would be no.
Yes, here's a question. So if we're looking at taking the derivatives, that's a function of x, right?
Sure.
This is also a function of x.
Okay, so I should take them separately.
Well, do we take them separately, or do we have a specific rule for when we have two functions?
No. No.
Like I said, these are hard problems. They're going to take you a while. That's what's going on.
Equally.
Online people, how's it going? You got an answer for E, but you couldn't possibly type it out. Right. Yep, that's probably about right. What about for part D? Part D is big. All right, you did it. Nice, nice. Oh yeah, no, I didn't simplify part D. No way should you be simplifying that. Yes. All right. Let's go over part D really quickly. Part D is not too hard. It's still pretty difficult, but compared to part E, it's considerably easier. So the idea with the chain rule is we're working our way from the outside in. Our outermost function on part D is this sine. We know the derivative of sine. It's cosine. And then we just leave the inside alone. But then we multiply by the derivative of the inside. Well, the derivative of tangent, we also know. Derivative of tangent is secant squared. Leave the inside alone. But then we also have to multiply by the inside of that. Derivative of e to the 2x would be e to the 2x multiplied by the inside of that, which is the derivative of 2x is 2. And then we have all kinds of closing parentheses. All right, so then if I wrote this out slightly nicer, it would be 2e to the 2x secant squared of e to the 2x times cosine of tangent e to the 2x. And hopefully I put all my parentheses in all the right places. And there you have it. That would be our derivative.
I think you added one extra parenthesis at the end.
I think I'm good. That one matches to that one. This one matches to
Oh,
this
okay, I
one.
didn't see that inner one.
Right, right. Yep. All right. So that's part D. Do you guys want a couple more minutes to finish part E? We got a couple people still working on it.
I'm broken.
You're broken. All right, perfect. All right, let's just go over part E then. So part E is long and complicated and probably cruel. But I think it's really helpful to see just how you would break down a problem like this. So first step, I look, what's my general shape? My general shape, I have one function of x being divided by another function of x. That tells me I need to use the quotient rule. I'm actually going to move this over. There we go. So the quotient rule says I need to take my bottom function, multiply by the derivative of my top function, subtract my top function times the derivative of my bottom function. All over my bottom function squared. All right, now I just need to find the derivative of my top function and the derivative of my bottom function. Well, then the derivative of this, here I have a function of x being multiplied by a function of x. So I need to use the product rule. The product rule says I should take the derivative of my first function. So then the derivative of x plus 3 cubed is 3 times x plus 3 squared times the derivative of x plus 3 is just 1. And then my second function is left alone, plus my first function left alone, multiplied by the derivative of my second function. The derivative of e to the 4x cubed by the chain rule would be e to the 4x cubed multiplied by the derivative of my inside part. So the derivative of 4x cubed, which is 12x squared. Oops. Yeah, we'll just leave it like this. All right. Actually, I should just leave that up. And that would be my derivative of this little bit here. Next, I need to find the derivative of sine of 8x plus 2. So using the chain rule, the derivative of sine is cosine. I leave the inside alone. And then I multiply by the derivative of the inside. So the derivative of 8x plus 2 is 8. And now I can just plug in these derivatives that I found into my first quotient rule. And that will give me sine of 8x plus 2 times 3 times x plus 3 squared e to the 4x cubed plus x plus 3 cubed times 12x e to the 4x cubed minus x plus 3 cubed times e to the 4x cubed times cosine 8x plus 2 times 8, all divided by sine squared 8x plus 2. All right. Any questions?
Can you take my exam for me Thursday?
I cannot take your exam for you, sorry.
Also, just to be fair, I think you should have to simplify for giving us that problem.
You think I should have to simplify? I could give you more example problems. Let's see. So just to recap this problem, what we did is we broke it down into smaller steps. First, we noticed we had to use the quotient rule. So that is what we did. We basically just put it in the general form of our quotient rule. We said our bottom function times the derivative of the top minus our top function times the derivative of the bottom over our bottom function squared. From there, we found the derivative of our top function by using the product rule. And within the product rule, we had to use the chain rule, technically twice, to take the derivative of x plus 3 cubed as well. And to find the derivative of our bottom function, again, just the chain rule right there. And then once we found these, we could plug them right back in over here and right here. And that gave us our final answer of all of this, which nobody wants to simplify. Question?
I think you said you didn't take this class, but do you think this would be a problem that would be found in the exam?
There is almost no way they would put a problem this hard on the exam.
You would need the hour just for that one problem.
Yeah, it's really just quite tedious. Are there any questions about this from the online people? All right. Cool. Let's see. I think we'll do maybe one more chain rule problem. It's going to be similar to part D. When they give you a problem like this with the limit definition. Oh my goodness. That's terrifying to think about. There is no way. I don't think any professor would have any fun solving that. It would take me probably several hours at least if I could get it. That would just be like a whole lot of algebra, honestly. Way too difficult. They would, yeah. There's no way they would give you a problem like this with the limit definition. Yeah. The hardest limit definition problems I've really seen are maybe some polynomials with some simple trig, maybe, at the hardest. This is terrifying to think about doing with the limit definition. All right. One last problem, and then we'll call it good. This one's not going to be too difficult. Let's see. I'm trying to pick which one I want to do.
At least it's not page 2.
All right, I think I should probably put in one of the square roots. Sure, we'll do it this way. Problem F. Is that good, or should I make it a bit easier?
I don't think it's that bad.
Don't think it's that bad?
That's just looking at it, it probably
All right. Remember, just take it one step at a time, work from the outside in. Good luck.
Shouldn't we know the derivative of Ln?
You guys know that?
I don't think I have.
Okay, if you haven't learned the derivative of natural log, that would make this one quite difficult.
That just may be me.
I was thinking to like, turn it into an E.
All right, you know what, we'll just ignore the ln bit. Try solving that. And maybe afterwards I'll run through the natural log one.
I'm just kind of at the point of simplification. Unless I did everything well.
You can't do also always do fractions. At least simplify your negative exponents, fractional exponents, the roots of one over things. Other than that,
I think simplification is usually where scribble moves. So,
we can always try and simplify the last one. Okay. So. this one. All right, so let's go ahead and go over this one since we are running short on time. So first off, we do have two separate functions of x. So we're going to start by using the product rule. And our product rule says we should take the derivative of our first times our second function left alone plus our first function multiplied by the derivative of our second function. Well, now I need to figure out what the derivative of the square root of cosine of x is. Well, we could always rewrite this. Instead of using a square root, we can rewrite it as cosine of x all to the power of 1/2. And now we can use our power rule. Bring down our power, decrease it by 1, and then multiply by the derivative of the inside. Our inside is cosine of x, so its derivative is negative sine of x. And then if I rewrote this, that would be 1/2 times negative sine of x times 1 over cosine of x to the 1/2, which is negative sine of x divided by 2 square root cosine of x. And this would be my derivative, so I can just plug it in right here. So then my final answer is 4 times the square root of cosine of x plus 4x times minus sine of x over 2 square root cosine of x. And I suppose one last little thing I could do, cancel that 2 with part of the 4, and also turn that negative and just say subtraction. That makes sense?
I think I did a lot of things.
It looks to me like you got most of it right. I think maybe
The simplification.
The simplification.
I got 2 over x minus sine x.
2 over x minus sine of x. Yeah, something went wrong there. Maybe you accidentally had your divided by cosine, square root cosine of x over here as well. Because then some things maybe would cancel when they shouldn't have. I can take a look if you want. But yeah, I said I was going to show you what would happen if we had the natural log around it. Natural logs are fairly easy because their derivative is just 1 over whatever's inside multiplied by the derivative of whatever's inside. So if we wanted to take the derivative of the natural log of 4x square root, what was it, cosine of x? Well, the derivative would be 1 over 4x root cosine of x. So the exact same inside. And then all we would do is, using modern marvels of technology, is multiply by all this. The derivative of 4x times square root cosine of x. All right. Perfect. Well, thank you all for coming to the week 6 review. Good luck on your exam. One other thing to note is, let me actually change what I'm sharing, is that there is an exam review tonight from 7:30 to 10:30. You can find it on the Student Success Center page. Let me just copy that link and paste it in the chat. I don't know if you guys want to go to it. It is entirely up to you. It's on the same page as the weekly review links, just under exam reviews. It's tonight. It's hosted by someone else. So tonight at 7:30 if you're interested. But other than that, thanks for coming and have a nice day.